Hello everyone and welcome to another video. So today I'd like to continue our discussion on flight mechanics by talking about two very important angles, namely the angle of attack and the angle of side slip, and how they're used to help us define two intermediate frames that are known as the stability frame and the wind frame. So before we get started, just at a very high level, we can conceptually think about this actually pretty easily. So to help with this, I've got a little demonstration. So I've got this fan here. Let's pretend that this fan, if I turn it on, is basically generating some local airflow. So the airflow is going, in this direction. And then let me grab a aircraft model. So I've got an aircraft, and I think intuitively, angle of attack makes a lot of sense. Basically, angle of attack is trying to quantify what is the angle of incidence of this local air as it's hitting the bottom or the top of the aircraft. So typically, angle of attack is defined to be positive, and we use the symbol alpha to define angle of attack. So alpha is positive if the air is hitting the underside of the vehicle. So what this would correspond to is a vehicle basically, flying along something like this, or relative motion-wise, the air is coming at it with this fan, etc., right? So conceptually, that's the idea of angle of attack, and that's, again, pretty simple. So this is a positive angle of attack because the air is hitting the underside of the aircraft. This would be a negative angle of attack because the air is hitting the top side of the aircraft. And again, one thing that's very important to note here is that angle of attack is really only dependent on what is the angle that the local body of the aircraft makes with the local wind field. So right now, this angle of attack is the same as if the wind field was tipped up and the aircraft was flat, right? Both of these have the same angle of attack because the angle that the air is making coincident to the aircraft body is the same in this orientation or in this orientation, right? Okay, so that's angle of attack. Angle of side slip is very similar. It's trying to quantify how is the angle or the local wind or the local velocity vector making with the aircraft body again, but now instead of in sort of the bottom or top, we're now interested on this, what side of the aircraft is it hitting. So again, the way to think about this, the way angle of side slip, and again the symbol beta is typically used for angle of side slip, is we say that the beta or the angle of side slip is positive if the local air hits the right side of the vehicle. So in this case, you can see the wind is coming on and it's hitting the right side of the aircraft effectively. So this is a positive angle of beta, and then this would be a negative beta because the wind is again hitting now the left side, okay? So conceptually, that's what angle of attack and angle of side slip, or alpha and beta, are. Let me turn this fan off so we can hear ourselves a little bit better. And let me get this out of the way so we can draw on the board a little bit more easily. So but that was sort of a high-level explanation of angle of attack and angle of side slip. So again, to help with this picture, I've drawn actual formal diagrams which are going to help us define these angles. So the blue axis is something we're already familiar with, right? We already talked about what is the body fixed frame, or FB. So I've labeled that in blue. So you can see the x-axis of the body frame. Again, the origin of this frame is at the center mass of the vehicle. The x-axis comes out the nose of the aircraft, the y-axis comes out the right wingtip of the aircraft, and the z-body makes a right-handed coordinate system pursuant to this x and y body location, right? So again, that's the same body frame we've been talking about in the past. Now, the way that we get to the stability frame, right, this other frame that we're talking about, is basically this stability frame is just related to the body frame through this angle of attack alpha, and we see that the body frame and the stability frame share the same y-axis. So the other way to think about this is that we go from the stability frame, or let's call it FS, to the body frame through rotating in a right-hand sense, right? Right-hand or right-handed rotation through the angle alpha, right, which is our angle of attack, about the shared y-axis, right? So the y body is the same as the y stability frame. right? Okay, so that's the definition of the stability frame. As you can see here, it's just nothing more than a rotation from the stability to the body by going through the angle of attack about the y-axis, right? Now, what's nice about that formulation is actually that's pretty much, again, like I said, it's a standard rotation about the shared y-axis. So in other words, if I wanted to write this down in terms of a rotation matrix, and again, this is maybe a great time to interject and say that make sure you've watched our video on expressing vectors in different frames using rotation matrices, because this is where we discuss the concept of rotation matrices about an x-axis, a y-axis, or a z-axis. Again, it's this video over here. If you haven't watched that, make sure you stop, view that, make sure you understand it, because I'm just going to write down the results and assume you're familiar with and comfortable with rotation matrices at this point. So again, getting back to our particular location, this is the same thing we talked about in the previous video. We're just rotating about a common y-axis. So again, if I want to write that in our notation of rotation matrix, right, this is going from the stability to the body frame through the angle alpha, right, the angle of attack, and all this is, it's just a right-handed rotation about the y-axis. So this rotation matrix is just going to look like, again, our normal 3 by 3, and since we're rotating about the y-axis, we're going to get the 1 here, right, and there's going to be all other zeros, and then this is going to be a cosine alpha, negative sine alpha, sine alpha, and then cosine alpha. Yes, cosine alpha. There we go. Okay, there we go. All right, and then likewise, let's talk about this this wind axis here. Okay, so the wind axis is again obtained by starting at the stability axis, which again I've drawn both stability axes sets in green, and now what you're doing is you are rotating from the stability to the wind axis in a right-handed sense through the angle beta, or their side slip angle, and you're rotating about the shared z-axis, right? The z wind and the z stability are the same. So again, what we're going to do here is we're going to go from stability frame to the wind frame, right? Which is and again, the wind frame is the frame that's aligned with the local wind vector. The x-axis of the wind frame is basically the direction that the wind is blowing and hitting the vehicle at, right? Okay, so again, we go from the stability to the wind frame by rotating in a right-handed sense through the angle of positive beta about the common z-axis, right? So now the z stability, or the z wind, is the same thing as the z stability frame, right? That's what that is here. So again, we can also think about going from the stability to the wind frame. You rotate through the angle beta, and again, it's nothing more than another 3 by 3 matrix, right? Right, where you rotate about the common z-axis, so the 1 shows up here, 1, 0, 0, 0, 0. Okay, and again, I want to make sure I get the sign of this thing right. Where did I put it? Okay, come on. Here we are. Yep. Okay, so this is now cosine beta, sine beta, minus sine beta, and then cosine beta. Right? Okay, so hopefully this gives us a picture of what is the stability frame, right? So we see the stability frame is this sort of intermediate frame, and we can either go from stability up to the body frame by rotating through alpha, or we can go from the stability frame to the wind frame by rotating through the side slip angle, right? So again, here's the clear pictures in sort of the appropriate planes. If you want to see it in 3 dimensions, I tried to sketch it. I'll show you a screen. This is my PowerPoint art of what this sort of looks like, and again, it's trying to make an isometric view of what you see here to hopefully provide just another viewpoint of this. But that's what I wanted to look at real quick. Now, what we should do is, if we're okay with this definition, there's a couple of things that we can notice right off the bat. So let's come here to this picture here, where we were looking at going from the stability to the body frame. Right? Now, what's interesting is if you look at this, remember the components of the velocity, and I wish I had another, maybe I will use, I don't have another color. I've used up all my colors. So I'll do this in black, I guess. Okay, so yeah, the velocity vector, right, of the wind, or the velocity vector of the vehicle, however you want to think about it, right? And in this, maybe I should mention right now, we're not considering any relative wind. I'm going to assume this vehicle is flying in perfectly still air, so the inertial velocity of the vehicle is basically the opposite of the relative air motion to the vehicle, all right? So in that case, what we can notice from this picture is that if this aircraft is flying along, right, the component of velocity projected onto the body x-axis, right, onto this axis, isn't that just what we were calling u earlier? Maybe what I should do is we should write this over here in the corner, right? We should say that the velocity of the vehicle expressed in the body frame, this is just UVW, right? This was just the x component of velocity, right? And we should maybe be a little careful. X body, right? And then the V is the Y body component of velocity, and W is the Z body component of velocity, right? So U is nothing more than the velocity vector which is projected onto this blue line. So maybe I'll call it this right here. So this is U, right? Okay? And similarly, the component of velocity projected onto this Z axis, right? Isn't that basically, it's this, right? So here's a right angle, right? So this is what we were calling W here, right? So now what's interesting is if you look at this right triangle that we've drawn, this alpha, we can quickly see is what? Tangent of alpha is opposite over adjacent, right? So tangent of alpha, here's opposite, it's W over U, right? So this is W over U, right? Or the other way you can think about this, right, is the inverse tangent of alpha, right? So alpha is basically tan inverse of W over U, right? And again, some red flags should probably be going off on your head. Anytime you see the inverse tangent, right, you got to remember this is not a 4-quadrant inverse tangent, right? So I would not recommend doing it this way, all right? Again, we had a completely separate video dedicated to discussing the 4-quadrant inverse tangent, or atan2, and other inverse trigonometric functions. So again, if you want to refresh your memory, feel free to check out this video. The link to it is in the description or in the card up above, right here in the upper right of the video. But again, this is not going to get you all of the information you need, right? The problem with this, right, is that, you know, if you had a U of, I don't know, let's make something up, 10 and a W of 3, right? So in this case, you clearly have a positive angle of attack, right? So that's the case where you got the vehicle. Well, I guess I don't need this little prop. I guess we drew it over here. This is consistent with a positive 10, right, velocity, and a positive 3 W component. So again, the vehicle is flying. It's flying along like this, right? Something like that, right? So you can see that the angle of attack alpha here is sure, if you were to plug in tangent inverse of, what is this, 3 over 10, you would get an answer. And again, oh gosh, I should have prepared this off screen. I don't actually have the numerical number. Tell you what, I will flash it up here, right? This is the numerical value of how many degrees this equals, right? Now, the problem is that, well, what if it was in an other situation? Like, what if you had this? What if this was your U component, right? And U was negative 10, and W was negative 3, right? So it's something like that, okay? So in this case, the vehicle is, so instead of flying this way, right, the vehicle is now going the other direction, right? And you might think that's completely ridiculous for a fixed-wing aircraft, and yes, maybe I will grant you that, but again, what if you have a vehicle which is highly maneuverable? What if this is tumbling or doing something like that? You could end up in a situation where the vehicle is going effectively backwards, right? Or, you know, nowadays, vertical lift systems or multi-rotor systems are very common, and this thing can just as easily go forward as it can go backwards. So again, we have to be able to account for these situations where your angle of attack could potentially be outside of the range of what a typical inverse tangent is going to give you, right? So you're going to need a full 4-quadrant inverse tangent to be able to capture both large positive angles of attack and large negative angles of attack, right? So what I'm getting at here is the problem is, in this case with the red, right, if you plug it into tangent inverse of -3 over -10, right, you see the whole problem, right? These two give you the same answer, right? Which is clearly not the case. In the black situation, the aircraft is flying, pretty normally, and in the red, it's completely not. It's actually 180 degrees different from the expected, or from the answer you're going to get here. So again, this is a problem with the standard inverse tangent. So the safer way to go about doing this, so again, I would X this out and say don't use this. Yeah, so the safer way to go about this is, instead of using the normal inverse tangent, I would use the 4-quadrant inverse tangent. And again, most ATAN2 implementations expect the Y component and then the X component, or again, I guess using our notation, I always have to draw this triangle. So here is your angle of interest here. This is the opposite, the adjacent. So ATAN2 is usually looking for this is the Y component, this is the X component, so to speak. So Y is really, it's the opposite over the an adjacent, so in this order. So in our case, we are looking for ATAN2 of the opposite side, which is the W in this case, and then U. There we go, right? So this is a better discussion or definition of angle of attack, right? So again, if you are given W and U, right? So again, if you know the velocity of the vehicle, right, expressed in the body frame, you take the inverse tangent of the W component and the U component like this. That'll give you a full 4-quadrant inverse tangent. So here, in this case, we'll see that alpha will be able to run between -pi and pi, right? Or between -180 degrees and 180 degrees, right? So again, you see that in this case, this gives you a full envelope calculation of alpha. So again, this will basically allow for those situations where, yeah, the vehicle is tumbling or moving backwards, or you have a multi-rotor which regularly does this and moves in all these crazy angles. So this is a nice, good, robust definition for angle of attack, right? Okay, so we can do something similar, right? In fact, if we want to look at the angle of side slip beta, right? Let's take a look at this. So angle of side slip. So again, we can look at a triangle. Now here again, what's nice about this triangle, if I draw a triangle like this, right? Okay, so let's assume that the component of velocity, which is on this axis, right? If you look at this, because this is the wind axis, the x-wind, the definition of the wind axis is that this x-axis is lined up with the direction of the relative wind. So the relative wind is coming at the vehicle along this red line, right? And the length of that's actually the airspeed, right? This is VA. So maybe we should say this is the airspeed of the vehicle, right? So if I look at this, we can write another expression, and we can say that what? Sine of the bank angle, or sorry, the angle of side slip. Sorry, I misspoke. That is not the bank angle. That is the angle of side slip, right? Sine. What is sine? Sine is opposite over hypotenuse, isn't it? It's opposite over hypotenuse. So in this case, the opposite, it's this component of velocity right here, this thing. Maybe I'm going to call this thing, let's call this V tilde for now, okay? So it is V tilde all over, and I guess the hypotenuse of this triangle, right, as we just argued, this is the actual total airspeed of the aircraft, right? So this is over VA, right? Okay, so now we got to ask ourselves, what is this v tilde? How is that related to u, v, or w, right? Now, what's great about this is if you look at this long enough, right, this is actually the same thing as the velocity component in the body y-axis, because both the stability and the body frame share the same y-axis, right? So if you think about this y-axis, this is the same thing as y body, right? Because we said that the stability, I'm pointing at the wrong, yeah, the stability and the wind frame, wait a second, yeah, they share the same y-axis, the stability. Oh, no, sorry, excuse me. Yes, that's exactly what I was looking for. The stability and the body frame, right? They share the same y-axis, right? That's exactly what we said here. So this y stability is the same thing as the y body axis, right? In other words, what it means is that this thing v tilde, this is the, maybe I should write this out. Isn't this the component of velocity along, in this case, look at the picture, right? Along the y stability frame, right? Because in green, right? I'm drawing this aligned with the y stability frame. But that's the exact same thing as the y body frame, right? So what is the component of velocity along the y body frame? That's exactly what we've got right here, right? We've been calling that v all along. So really, v tilde is the same thing as v, right? So really, we have, again, this nice relationship now that sine beta, it's actually just v all over va, right? The airspeed, right? And again, I think everyone will agree that the airspeed, right? It's just the vector norm of these components, right? In other words, va, right? It's just u squared plus v squared plus w squared square rooted, right? Because the whole idea with the wind frame is that it is aligned with the velocity vector of the wind, right? So it's all these components together. It's all stacked up. This is the airspeed, right? So here we go. We end up with, yeah, this is actually a really darn convenient relationship for beta, right? And again, we could go ahead and now take the inverse sine of this if I want to really isolate beta. So again, maybe I prematurely boxed this up. I got a little excited, but I guess we really could write that here. Beta is arc sine or a sine or however you want. Maybe I'll use yeah, sure, I'll use MATLAB speak. A sine of v all over VA, right? Here we go. And again, some alarm bells might be ringing in your head here because, again, we discussed that, yes, the inverse sine, right? This is only going to really yield values that are basically within negative pi over 2 to pi over 2, right? Or within the value of negative 90 degrees to positive 90 degrees. Right? Because again, if you plot this a sine, right, what does inverse sine sort of look like? So if you look at, you know, beta on this axis, and then you plot v over VA, right? This thing looks like this, right? Between -1 and +1, it's basically like this, right? Where you end up with up here. Right, yeah, this is like pi over 2 and then minus pi over 2, right? So this formulation is only going to get you angles of side slip between -90 and +90, which actually is totally fine for our purposes because, again, this is basically the similar situation where think about this. We've got a wind vector. Let me pull up my prop here. What we're trying to do is we're trying to be able to describe a velocity vector of any velocity vector coming at this vehicle at any potential direction, right? At any possible points around this sphere. So you can think about like a sphere around this aircraft. The wind velocity vector could be coming at this at any potential direction, right, along this sphere. It's almost like the Earth, right? Think about the sphere as the Earth, right? How do we describe any location along the surface of the Earth that's coming down towards the center of the Earth, which is this aircraft, if you want to think about it that way, right? So it's almost like we basically have a longitude-latitude system is kind of how you can think of the angle of attack and the angle of sideslip. So the angle of attack, right, this is almost like the situation in Earth where you have a longitude bound, right, which is in the range of minus 180 degrees to positive 180 degrees, and angle of sideslip is like a latitude bound, right? Where you have latitudes which are between negative 90 degrees and positive 90 degrees, right? And with this set of mappings, right, with those angles, if you tell me the lat and long, I can find any location on that sphere, right? It doesn't matter that the latitude only runs between negative 90 and positive 90 because the longitude runs between negative 180 to a positive 180. It's the same case here. Just substitute, angle of attack is kind of similar to longitude, and angle of sideslip beta is kind of similar to latitude in this sense of having these bounds, right? Okay, so, all right, I hope that's reasonable. Again, I think the thing that we wanted to get out of this are several pieces of information. It's this rotation matrix to go from the stability to the body axis, this rotation matrix to go from the stability to the wind axis, and then this definition of angle of attack. So now if someone gives you W and U, you can basically compute the angle of attack using this 4-quadrant inverse tangent, and similarly you can also compute the angle of sideslip. So those are the 4 pieces of information that were relevant in this discussion. So tell you what, give me a second to erase the board, and we'll take it one step further. All right, so the next natural thing to do is to say, all right, if we have these 2 individual rotation matrices, how about let's go all the way from the body all the way to the wind axis, right? So again, that's pretty simple to do. So if we want to look at rotating from the let's go the other way. Let's go from the wind to the body axis, right? This is just going to be a function of both angle of attack and angle of sideslip, and all I need to do is just basically put together these rotation matrices, right? So I'm going to go first from the wind to the stability frame, right? And this was over the angle alpha, right? That's this guy right here. Oh, sorry, no, wait a second, sorry. No, sorry, this is beta. Sorry. This is angle of sideslip, right? Yep, here we go. And furthermore, note that we got to be real careful that these are actually not the same, right? There's a transpose. So again, we'll maybe make a quick note here just to be very careful. Remember that if I want to go from the wind to the stability frame through the angle beta, right? It's basically this matrix here, which is actually going the other direction, is going from stability to wind over beta, and I need to take the transpose, or basically it's inverse, right? The C looks weird. Right? Okay, so that will get me this matrix, and then what I need to do is I need to go now from the stability to the wind frame over the angle of attack alpha, right? And no, sorry, sorry, I keep goofing up these subscripts. Stability of the body, right? Because I eventually want to go from wind to the body, or from wind to the body. There we go. And this guy right here, that is actually exactly what we already have. So that's perfect. I basically just got to plug these things in, do a little bit of transposing, etc., etc. You end up with this thing. Just for completeness, maybe let's write this thing out. Again, it's a bit of a bigger 3x3 in this case. Right, but really it's nothing more than matrix multiplication. Feel free to go over to Mathematic and do this if you're interested, but this is going to be, I want to make sure I got, wait a second. Yep, this one right here I want from wind to body. Yep, okay, so this is going to be cosine alpha, cosine beta. This one is negative cosine alpha, sine beta, negative sine, alpha, right? sine beta, cosine beta, 0, cosine beta, sine alpha, negative sine alpha, sine beta, and then cosine alpha, right? Okay? And again, if you want to go the other direction, it's just the transpose, right? So if I want the rotation matrix to go from the body to the wind axis, right, over alpha beta, it's just the transpose of this matrix. And again, let me just write that up for completeness, because this is the form that you may see in other documentation. So for example, like in MATLAB's implementation of a direction cosine matrix to go from the body to the wind axis, there's a documentation page. In fact, I'll flash a screenshot from that so you can see that's what they claim it is. And again, if you just take the transpose of this, heck, we can do this right now, right? It's cosine alpha. Let me get the diagonals. The diagonals stay the same, right? Cosine beta, cosine alpha, and then I need to just start flopping these guys, right? So this becomes a sine beta, sine alpha, negative cosine alpha, sine beta, negative sine alpha, sine beta, negative sine alpha, 0, and then, oh yeah, we got the cosine. Okay, great. So this matches up with that, as you can see from MathWorks' documentation page. And again, you can clearly see now where they get that from, where the texts like Stevens and Lewis get this from. It's all basically just composing these rotation matrices together, right? All right, so I cleared some space. I left this particular definition of the rotation matrix up, where we go from wind to body, because what I want to do now is I want to derive some expressions of how are u, v, and w related to these aerodynamic angles of attack and side slip, okay? So the way we can do that, and it's actually quite simple, is we can just make the observation, right, that we said the whole idea with the wind frame, right? What's the velocity vector of the vehicle expressed in the wind frame? Well, that is simply the airspeed is aligned with the x-axis, and you have no velocity in any of these other y wind or z wind axis, right? So this is what the velocity of the aircraft is. It's actually super easy to express in the wind frame, right? Because the whole point of the wind frame is its x-axis is aligned with the relative wind, which is basically the direction that the aircraft's center of mass is headed. So again, I think I'm beating a dead white horse right now. I'm belaboring the fact. I think everyone understands what this is doing, right? This is the way to write the velocity vector of the airplane expressed in the wind frame. Is pretty simple. So if I want the velocity vector of the aircraft expressed in the body frame, I just need to go from the wind frame to the body frame. So that's really simple. Like we have, it's right there. It's the velocity of the aircraft in the body frame. It's nothing more than the velocity of the aircraft in the wind frame, and then I just need to rotate from the wind to the body frame through alpha and beta, right? So basically, jam this 3x3 matrix in over here, jam this really simple 3x1, and you can see what that's going to do. It's only going to pick up basically this first column, right? And we end up with, again, let's write the left-hand side of this, V expressed in the body frame. Well, V expressed in the body frame, that's just UVW. So we end up with UVW is just equal to basically this first column multiplied by the airspeed, right? So you end up with, this is just VA cosine, what is it, alpha cosine beta. And then V is just VA times sine of beta, right? And finally, W is just VA times this guy, right? This is cosine beta sine alpha. Right? And in fact, then we can get rid of this matrix form maybe. Let's get I'll just make the first row equal the first row, right? So here's an expression for U, here's an expression for V, here's an expression for W. So here you go. Here's three equations which basically give you a mapping from if you know what the airspeed and the angle of attack and the angle of side slip are, you can calculate U, V, and W very easily right here, right? So this is, you can think, let's call this maybe like a forward mapping or a forward transformation. right? It basically allows you to go from the states of angle of attack, airspeed, angle of attack, and beta, and it will allow you to transform into UVW, right? Now, how about the backwards transformation? What if we had, yeah, I could go ahead and erase that, I think. I want to now get the sort of the reverse transformation. So in other words, what if we had UVW, and I now want to get the airspeed, alpha, and beta, right? Well, you know, we actually already did this. So there's a couple of ways we can skin this cat right now. One way we could do this is, well, I'll tell you what, we already did this, in fact, right? We said that the airspeed, it's just u squared plus v squared plus w squared square rooted, right? And we said the angle of attack, in fact, shoot, I just erased it, and that was our whole discussion of the 4-quadrant inverse tangent. Just for, I guess, for completeness, I'll rewrite it up here. This was really easy. It was a tan 2 of W and U. And again, we got to be careful with the way that a tan 2 works. Is this, I'm assuming that a tan 2 expects the y component and then the x component. Again, you read the manual on some software implementations of a tan 2 and they want this thing flipped. For example, in Mathematica, they wanted the other direction. MATLAB wants it in this direction. So again, just be cognizant of what software package you are using. Okay, and then beta, we said, was inverse sine of, I think it was V over VA, which we can kind of quickly see right here. And I guess to make this completely normal looking, plus W squared square rooted, right? This was just the airspeed in the denominator, right? Right, and I just want to again double check to make sure we are doing this correctly. Yeah, great. Okay, so here's one way to go about doing this inverse mapping. Again, we saw that this was not a completely unique mapping. Right, due to some of these ambiguities with the non-one-to-oneness of the a tan function and the a sine function, right? So another way you could do this is, I guess you could actually try to go and brute force it. Like, here's one transformation. You can go to like a symbolic manipulation package like Mathematica and just say, hey, Mathematica, solve these 3 equations for the 3 unknowns. Basically, solve it for VA, alpha, and beta. In fact, I'll save you the time. I did that over here. Here's a screenshot of it. As you can see, there's actually, I think there's 4 different families of solutions, and they effectively give you these answers. Although what's interesting about that is we also come out with another relationship. In fact, if you look at that screenshot and you plug and you pull out the, you know, for example, that 4th solution, you'll actually see that another way you could write this beta is you could also write this as a tan 2 of V and then square root of U squared plus W squared. So both of these beta definitions are valid. They will work. They should give you the same answer. It's just a question of which one do you want to use. Again, there are potential issues, I guess, that you need to be aware of with each of these. Remember, we said a sine is only going to give you between positive and negative 90 degrees, which was fine in this case. This is a full 4-quadrant inverse tangent, but again, if you stare at this thing and you notice this second argument is never ever going to be negative. So again, you might have to look at that Mathematica output and you'll see that it takes this into account in some of its discussions and some of these other solutions where you'll see negative signs pop up in front of this. So again, I think this is probably more than we need to do. This is a perfectly fine and sufficient set of transformations. So I think what I would take to the bank is, here's the forward transformation. This is pretty bulletproof. You can't argue with this. And then this one is a perfectly valid set of inverse, reverse transformations that are implemented all the time and work quite well. Okay, so tell you what, again, give me a second to erase the board. Let's have a couple of discussions now on why did we spend all this time doing all of this. All right, so why do we need all this discussion of the stability frame and the wind frame? I mean, don't we just need stuff in the body frame? Why complicate matters? Well, that's exactly the problem, is that sometimes it does get complicated. Remember when we talked about our equations of motion? Yes, we need a lot of our forces to be resolved into the body frame so that we can plug that into our equations of motion and understand the dynamics of the system. Now, however, the data that you may get for characterizing the aerodynamic forces and moments on this vehicle might come in one of these other frames. So for example, let me draw, like, how about an aircraft in a wind tunnel or something like that? Again, I'll make it going this direction instead, just to get a little bit of extra practice. So again, right, we have a body frame. Here's an X body and then a Z body. And I guess the Y body is that's going into the page, right? So here's the Y body frame, right? Okay, now this is flying along, and to make things easier, let's just assume that beta is equal to 0, because I can't draw very easily things in and out of the plane. So let's say that this is flying along and you got your wind coming at you like such, right? So we have, in this case, you can see that here is your X wind frame and here is your Z wind frame. And I guess in this case, because right, we've got beta is equal to 0, that the Y wind frame is also in that direction, right? Now, what's interesting is that, let's think about this. I would like to get, for example, let's just look at the aerodynamic forces of the vehicle. Well, the whole question becomes now, where are these aerodynamic forces going to be expressed in? How are you even going to understand this? Where are you going to get, what does the aerodynamic force of this vehicle look like? And again, I'm sure anyone who's ever driven down the road and stuck your hand out and moved up and down, you know that as you change the angle of attack of your hand, it definitely influences the aerodynamic forces on this vehicle. And similarly for angle of side slip, right? What I'm getting at, this is my long-winded way of saying that typically you'll probably go to like a wind tunnel to try to characterize some of these first order effects of how does the aerodynamic force vary as a function of angle of attack and angle of side slip, right? So in other words, it's very easy to express this in the wind frame, because what a wind tunnel is simply going to do is going to give you the lift and the drag and the side force that's acting on this object, right? And typically, right, isn't lift typically defined as this, right? So this is a positive lift, right? Which you can see is actually sort of aligned in the negative Z direction, right? So the aerodynamic force expressed in the wind frame, the Z component is actually negative lift. Right? So if the wind tunnel comes back and or somebody tells you, an aerodynamicist or a CFD guy tells you, oh yeah, the lift at this condition, you know, at a certain angle of attack is positive 500 pounds, right? You as a simulation or a flight mechanics engineer know that, okay, the aerodynamic force expressed in the wind frame, its third component is actually negative 500, right? And similarly, where's drag? Positive drag is usually backwards, right? Here's positive drag. Right? So positive drag is usually a force that's retarding the direction of motion. But again, you look at how is this thing aligned with any of these frames? Oh look, it's actually conveniently, it's aligned with the X wind frame, but again, it's in the opposite direction. So again, what you have here is this is negative drag. Right? And then side force, I guess it depends where you go and who's going to give it to you. For the interest of argument, why don't we say that side force, or a positive side force, is into the page, right? It's pushing towards the, in this case, I guess it would be the tunnel wall, the right-hand tunnel wall, the wind tunnel wall, which is closest to the other side of the vehicle. And again, shameless plug, we will be going into a lot more detail in wind tunnel testing and discussion in some future videos. But for now, I think we can say that what you can do is, if again the wind tunnel comes back and tells you here's how much side force you're experiencing, you can put that in here as positive SF, right? So again, the reason this is so helpful is, or the reason we need these wind frame or stability frame, is because if somebody gives you this data set of here's how the drag, side force, and lift, how are these all a function of alpha and beta, right? we have to ask which frame are these expressed in, and most likely the wind tunnel or some other person is going to give these forces to you expressed in the wind frame. Well, us as GNC engineers or as flight simulation engineers, we need to be able to take that data in the wind frame and express it into the body frame for our equations of motion. And again, we now know how to do that. I can get now the aerodynamic forces expressed in the body frame. If somebody tells me the aerodynamic forces expressed in the wind frame right here, I just need to rotate from the wind frame to the body frame through the angle of attack and the angle of side slip, right? And there you go. Now, again, I don't want to make it sound too simple, because all this is doing is if you think about this, usually what we're looking at here, in fact, you can almost see it by our notation, is we are really looking for, or what we're characterizing here is, how do these aerodynamic forces depend on angle of attack and angle of side slip? And again, those are usually primarily two of the main, let's just focus on lift. Lift is usually a strong function of angle of attack and angle of side slip. It's also a strong function of other variables like your dynamic pressure or your Mach number, or even unsteady aerodynamics like your pitch rate might matter here, right? So a lot of the times what you're going to get in the wind tunnel is only going to be the steady state aerodynamic effects, not necessarily these unsteady aerodynamics effects or linear effects or any of these other higher order effects. So again, I think we're getting ahead of ourselves. We will talk a little bit more about that in our wind tunnel testing discussion, but for this discussion on the alpha, beta, and the stability in the wind axis, I think this is a good spot to leave it, because I think we've fully covered now what the angle of attack alpha is, what the angle of side slip beta is, and how they're used to define the intermediate stability frame and the wind frame, and again, how to get that everything back to the body frame. So again, like I said, I think this is probably a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. It really does help me continue making these videos. Another way you can support the channel is also via Patreon. I do want to take a moment and thank some of our existing patrons. They support the channel, and 100% of the proceeds the channel receives via Patreon are directed towards K through 12 education for young adults and kids. So, and again, speaking of the new videos, remember, they come out every Monday, so I hope I'll be able to catch you at one of these future discussions and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.